Hi everyone, we are Group 7 and in this video we will be looking at the concept of molecular orbital theory. Today I'll be talking about forming molecular orbitals when it comes to linear combinations of atomic orbitals. Dev, Dan, and Harvey will then bring you through sigma and pi bonds. After that, Jess, Molly, and Aruj will talk you through molecular diagrams and bond order. Devani will then go over the HOMO-LUMO gap, which will follow with Fion comparing the molecular orbital theory to the Lewis structure theory. Lastly, Minodora will talk about some exceptions to the theory such as nitrogen and oxygen. So far, we've used Lewis structures to represent covalent bonding. Here, a chemical bond is described by a pair of electrons shared between two atoms. The molecular orbital theory looks at bonding slightly differently. Instead of electrons being shared between two atoms, those electrons are instead assigned to molecular orbitals, which are formed by the overlap of atomic orbitals. This overlap can only happen under certain conditions. The atomic orbitals in question must be comparable in energy to react. If the energies vary greatly, the bonding can be considered as ionic. The atomic orbitals must also have the same symmetry with respect to the bond axis. If these two requirements are met, a molecular orbital with two nuclei can be formed. In this case, we're going to be talking about a simple diatomic molecule. Let's take hydrogen as an example. Here we have two hydrogen atoms. In order to combine them into one molecular orbital, we need to linearly combine the atomic orbitals. Each atom has one electron each, which reside in the 1s orbital. These orbitals can combine in either a constructive or destructive manner in phase or out of phase. If these orbitals combine constructively, there's now an electron density between these two atoms. We now have a chemical bond described as a sigma bond. If these orbitals combine destructively, there will be no electron density between the two atoms. This results in a nodal plane, which is perpendicular to the bond axis. Instead, the electron density faces away from the bonding orbitals. This is called an antibonding sigma bond. Note that the total number of molecular orbitals is equal to the number of atomic orbitals used to make them.
So now we're going to start looking at the bonding and antibonding of s orbitals. So at the top, we have two s orbitals that are spherical in shape, and they are on the same side of the wave function. So when they bond over the bond axis, they'll form a lobe that looks like this, and this is the bonding molecular orbital. And when we have two s orbitals that are on opposite sides of the wave function, and they bond together over the bond axis, a nodal plane is formed between them here, and the electron density shifts to each side over here and over here, as there's no electron density between the two, or there's no electron density on the nodal plane. Now, as for p orbitals, you can have sigma bonding and sigma antibonding. So for the sigma bonding, when two of the lobes are on the same side of the wave function and they collide together over the bond axis, we get a molecular orbital that looks like this, where there is two nodal planes here and here. And when we have an antibonding sigma p orbital, we have two lobes that look like this, and there is a nodal plane between the two, as the signs of the wave function are opposite. Now, when we go into side-on overlap, so in other words, this is a pi molecular orbital. When they collide, when the p orbitals are rotated in a different way, such as these have been rotated 90 degrees, we get a pi bonding orbital, and there is a nodal plane between the two, here like so. And when we have a pi antibonding molecular orbital, there are two nodal planes that cross together perpendicular to each other, and electron density shifts to the corners, like so here.
In order for orbitals to overlap, they must have a similar energy and symmetry. When a pair of starting orbitals have different symmetries about the bond axis, e.g. sigma and pi, there is no overlap and no molecular orbitals can be formed. In the first example, the sigma orbital's wave function stays the same above and below. The px orbital, that wave function is different above and below. So therefore, there can be no molecular orbitals formed and this is called disallowed overlaps. In the second example, the PZ orbital has sigma symmetry, whereas the PX orbital has pi symmetry. So due to there being different symmetries, there can be no molecular orbitals formed. Similar with the last example, the DXZ orbital has pi symmetry, whereas the PX orbital has sigma symmetry. So the symmetries don't match. So then again, there's no molecular orbitals that can be formed.
sp mixing is where orbitals of the same symmetry and similar energy interact with each other. One orbital increases in energy and one decreases in energy. For sigma antibonding, the wave functions are opposing on the s and p orbital. This forms a nodal plane on the x-axis, and the lobe closest to the nodal plane on the p orbital gets smaller and the electron density is shifted to the right. For sigma bonding, the wave functions are on the same wavelength, so they overlap, causing one lobe on the sp orbital to be bigger. Because it has the same cylindrical symmetry, overlap is therefore possible.
As you can see, this video is all about molecular orbital diagrams and bond order. Bond order is the number of chemical bonds between a pair of atoms. It indicates the stability of a bond. The higher the bond order, the more electrons holding the atoms together, giving it a greater stability. You can work out the bond order by taking away the number of electrons in the bonding MO from the number of electrons in the anti-bonding MO, then dividing it all by 2. A partial double bond is formed because of the resonance structure, meaning it will have the characteristics of a single and a double bond. Molecular orbital diagrams predict the physical and chemical properties of a molecule, such as shape, bond energy, bond length, and bond angle. Here we have an MO diagram for hydrogen. On the diagram, you can see that the anti-bonding orbital is at a higher level than the hydrogen atomic orbitals, which are located at the sides, and the bonding orbitals are at a lower energy level. Electrons are placed into molecular orbitals using the Arfbol principle, Pauli exclusion principle, and Hund's rule. If you need a reminder on what these are, they're at the top right corner of this slide. In H2, there are 2 electrons, one from each hydrogen atom. As the diagram shows, these are both in the bonding orbital, with their spins paired. This is a helium molecular orbital bond diagram. The helium atomic orbitals are located at the left and right, with the molecular orbitals found in the middle. 2 electrons are given from each atom, giving us a total of 4 electrons. And when we use the principles from the previous slide to fill the diagram, you can see that 2 electrons are paired in the bonding orbital, as well as 2 electrons paired in the anti-bonding orbital. If you recall the equation for bond order, you should be able to work out that the bond order is 0. This is because helium has a noble gas configuration and can exist as single atoms.
Now moving on to HOMO-LUMO. As shown in the diagram on the left, HOMO is the highest energy molecular orbital that has electrons in it, and LUMO is the next highest energy molecular orbital that doesn't have any electron in it. The HOMO-LUMO gap is simply the energy difference between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. The wave function, given Greek letter psi, describes the position of an electron in the orbital, and psi square gives the electron probability distribution for electrons in each orbitals and is related to the shape of orbitals. HOMO-LUMO electronic transition. The HOMO-LUMO transition has the lowest possible energy difference. For the diagram on the left, electron transition from wave function 4 to wave function 5 has the lowest energy gap, i.e., it is the HOMO-LUMO gap. When the molecule is exposed to a wavelength of light with energy corresponding to delta E, which is the HOMO-LUMO energy gap, this wavelength will be absorbed and the energy is used to transition one of the electron from the HOMO to the LUMO. The energy difference, delta E, of the gap can be calculated by multiplying Planck's constant by the frequency of the photon. This electron transition gives rise to UV and visible absorption and emission spectrums. The difference in energy between HOMO and LUMO can be used to predict the strength and stability of transition metal complexes as well as the colors they produce in solutions. HOMO-LUMO gap of conjugated systems. As you can see on the diagram, the conjugated system is increasing in size from left to right. The HOMO-LUMO gap decreases as the size of conjugated pi system increases. The wavelength of these increasing conjugated system also increases, meaning the energy required to excite an electron from ground state decreases. Smaller alkenes have delta E corresponding to UV photons, whereas larger conjugated molecules have delta E corresponding to visible photons. As the HOMO-LUMO gap gets smaller, the energy difference decreases and the wavelength of photons required to excite an electron from HOMO to LUMO increases. The longer the photon's wavelength, the lower its energy, i.e., towards the visible light spectrum. As the energy gap, delta E, gets smaller between HOMO and LUMO, the length of conjugated chain increases. In chemical analysis, absorption spectroscopy can be used due to its specificity. Because molecules have specific HOMO-LUMO gap, the energy required to excite an electron from ground state is also specific. This means the wavelength of photon needed for electronic transition is specific to the energy gap. A UV visible spectrum is produced which shows the absorbance of light at particular wavelength.
Comparing MO theory to Lewis structure theory. Covalent bonding in Lewis theory shows electrons being shared between two atoms. Molecular orbital theory allocates the electrons to molecular orbitals. Lewis theory is based upon orbitals around a single nuclei, whereas molecular orbital theory is based upon orbitals between two nuclei. This means that molecular orbital theory takes into account the interaction between the two nuclei. In the case of an oxygen molecule, both theories predict a double bond. Lewis theory predicts an oxygen molecule to have all its electrons paired, therefore the molecule would be diamagnetic. MO theory predicts the molecule to have two unpaired electrons, therefore the molecule would be paramagnetic. This video shows oxygen is in fact paramagnetic, suggesting it contains one or more unpaired electrons.
The way oxygen behaves is called paramagnetism. That's a fancy way of saying that each molecule of oxygen is attracted to a magnet's magnetic field. So, when I pour the liquid oxygen between the poles of the magnet, it sticks. And we can even make a little bridge out of liquid oxygen that'll stay there until the oxygen finally boils away.
This property proves that Lewis theory is not always adequate for predicting the behavior of molecules.
Let's have a look at molecular orbital diagrams for nitrogen and oxygen molecules. When sketching the molecular orbital diagram for the molecule of oxygen, we start filling the orbitals with electrons in order of increasing energy from sigma 2s to sigma star 2s, then sigma 2p, pi 2p, pi star 2p, and the last one, sigma star 2p, which is the highest in energy. We can observe that oxygen atoms have in their 2px orbitals two paired electrons. If we have a look at nitrogen molecule, the bonding molecular orbital sigma 2p is higher in energy than pi 2p bonding orbital, and sigma star 2p is much higher than in oxygen's case. Also, sigma 2s and sigma star 2s are lower in energy. Why? This is called sp mixing. For nitrogen, all p orbitals have each one unpaired electron only, hence the energy of these orbitals is not too high but similar to energy of the 2s orbitals. If two orbitals have similar energy, they can combine. In this way, wave function of sigma 2s orbital combine with wave function of sigma 2p orbital in such way that sigma 2s orbital become more stable and sigma 2p orbital becomes less stable. As a result, sigma star 2s and sigma 2s are lowered in energy, and sigma 2p and sigma star 2p are going up in energy, so that they become higher in energy than pi 2p orbital and pi star 2p orbital. Keep in mind that sp mixing occurs only in case the orbitals have similar energy so that they can combine. This sp mixing occurs as well for carbon, boron, beryllium, and lithium because of atomic orbitals having unpaired electrons or being vacant. Why is oxygen not adhering to this rule? Well, oxygen as well as fluorine has paired electrons in the p orbitals. Hence, the orbitals have much higher energy than the 2s orbitals. But we know that sp mixing only occurs between orbitals of close energy.